Great. So previously we discussed the fundamental theorem of line integrals. And now we're going to get into Green's theorem. So remember that 2 lectures ago we discussed integrals of the type C, F, R, T, dt, right? And I said that this is, well, we can just say that this is dr. This whole thing is dr. And so this could also just be written as f dr, right? Where the understanding is that f is evaluated along a curve rt that parameterizes c. So f is also, you can think of as rt dr, right? It's no different. Not writing the rt is no different than if you didn't write x when you write f of x. You could just write f. Okay, so sometimes we have this sort of thing. Sometimes we have this. And if you think back to that video where I split the integral up into 2 parts, I believe it was orange and red, and orange was an arc that was equal to 0, and then it had this straight line, and I broke that up into 2 parts, dx and dy. Well, I said sometimes it's sometimes helpful to integrate the dx. You convert the dx to dx by dt times dt, and you evaluate the integral. You replace all instances of x with your parameterized curve, and you integrate with respect to t. But sometimes that's a lot of work. So we're going to go through some examples in this video. So there's this thing called Green's theorem, and naturally, because it's Green's theorem, I had to write the word in green. And what it says is that the integral around this curve, you have some curve, C, and that if you integrate that, now notice it's counterclockwise. So the standard for this is counterclockwise. When you have this curve, you're going to pick up a domain, and the domain is everything inside that curve. So this is a closed curve. That's the other thing. The curve has to be closed. Okay, and I called those loops when I first started, but we're going to call them closed curves from now on. Okay, so what it says is that if you have this form p dx plus q dy, you can convert an integral on the boundary of a domain to the integral over that domain like this. Now, in some sense, you can think of this domain and the boundary as a derivative, right? So you have this space, and the domain is its derivative. So the boundary is its derivative. So we're passing the derivative here to the inside and doing it to the function instead. Okay? Why can I think of the boundary as a derivative? Well, that's a little deep. That would require us going further into higher order mathematics, but just trust me. Now, this on this side, we can do this. We know how to do double integrals. We've done lots of them. That was all of exam 2. So what it says is that, well, p comes first. Now you're going to put q. So you're going to put del q by del x minus del p by del y. Now this should look familiar. Well, it turns out that, remember, if you have a conservative vector field, you have del p by del y equals del q by del x. So what does this tell us? Well, if you have a conservative vector field, then this whole thing is going to equal 0, but then that's going to equal 0. But that's really not a surprise, because I previously said that if you have a conservative vector field, the closed loop is going to equal 0. right? Because you start and finish at the same spot, and by the fundamental theorem of line integrals, you can take f of little f of that point minus the final point, initial minus final, but they're the same thing, so it's equal to 0. Okay, well, anyway, my only point is that this is not a surprise that this should equal 0 for a conservative vector field, but regardless, you don't care about that. Let's do an example. So our function is that this right here, and we have a rectangle, and we want to consider the curve. We want to consider the curve that goes from 0, 0 to 5, 0 to 5, 4 to 0, 4 to the origin. So we have this loop, and the question is, what is this integral? Now, not all loops are going to give us 0, only if it's conservative. So this is not conservative, right? Because I can look at my function, right? So f equals pq, this is equal to y squared and x y. If I take the derivative of p with respect to y, I get 2y. If I take it with respect to, if I take the second coordinate with respect to x, I get 2xy. 2xy does not equal 2y, except in certain cases if x is 0. So this is not conservative. Okay, but what it does say is that this really nasty integral, which I could do going back to the first definition of what that means, just, right? This is curve 1, curve 2, curve 3, curve 4, right? Come up with parameterizations for them. Along here, you say let x equal t, y is equal to 0. Up here, you say let x equal 5, let y equal t. Here, and so on, right? And then you vary the values and you compute all these things. We could do it. I'm not going to do it in this video because it's going to distract us, but it's a lot of work. It could be done by the definition. Does that make sense? Good. Well, I don't want to do that. That's a pain in the butt. So what we're going to do instead is we're going to use this right here. So this is my P, and this is my Q. So what I need to do is rewrite this, and I'm going to take the derivative of this with respect to x, so I get 2xy minus this with respect to y, which is 2y, and I'm going to integrate it over this square, or sorry, this rectangle. Well, it's not really that complicated. We know exactly what that looks like. So I'm going to go ahead and replace that and put down actual coordinates. So this is going to be 0 to 5 for x and 0 to 4 for y. dx dy. And I'm not going to compute that because that's very straightforward, but that's the idea. Now you notice that's not a lot of work. You can do that. That would take no time at all, maybe 2 minutes. But this original thing, doing it by definition, would be, who knows, it would require a lot more hard thinking. We don't like to do that. We like to keep things easy, so that's why we like Green's theorem. See you in the next video.